what we're going to be going over here is a linear programming example. We're going to be optimizing some profits and also minimizing costs here. And really what we're going to be doing is allocating manufacturing resources. So this is going to be our problem here, and I'm showing this data here that we're going to deal with. We're going to, and the things we want to point out on it here is our material costs and our labor costs. Those are going to be all variable costs, and we're going to be allocating these. And then we have some overhead costs, and those are going to be fixed costs, and they're really omitted here from our linear programming problem here, or our example, because they're not affected by any levels of our products that we're going to be selling here, plus the material and labor. They're fixed. So we would include those here when we calculate our overall profit, but for our linear programming problem, any fixed costs here we're not going to include. And then we're going to have a sales price, and we're really dealing with two different products here, product P and product Q. And then we're going to have some usage for product P and product Q for the direct materials, direct labors, and then they're going to be going through two different machines here, machine A and machine B here. So we've got what we call the demand constraints that we have listed for each of those products. And then we're also going to have some other constraints here, and they're going to be for machining hours that are available for those two different machines that I'm showing here. And those are our supply or resource constraints that we'll be looking at. Okay, so the first thing we want to do is we want to set up an objective function here, and that's really we're looking at when you're dealing with this profit maximization, you're dealing with cost accounting here. What you want to do is you want to be maximizing the contribution margin here, and that's really looking at your revenues here less your variable costs. So for our objective function here, that'll be a total contribution margin that we're going to try to maximize in this case. And let's just look at how we develop that here. So first for our revenues, we got those two different products, P and Q here. So we take the sales price for each of those here times whatever quantity. The sales price here for P is $76, for Q is $66. So we take those prices times whatever quantity we're going to have for both of those products that we're going to sell for. We add those together here, and then we subtract the variable costs from those. And that is our material here and our labor. So let's go up and look at it. So our material is $10 a pound here, and our labor cost is $26 an hour. So those quantities here, $10 times material, and $26 times our labor here, and we're going to be subtracting that from our objective function here. All right. So the next thing we have to deal with is our capacity constraints here. So we're going to have those two different machines here, and then we're going to have material and labor constraints. So let's go and let's set those up here. So for our machine A, let's go and look at that here. Product P is going to use 1 hour. Product Q is going to use 1 hour here. So in our constraints here, do we 1 times P, a coefficient here, 1 times P and 1 times Q, add those two together, and they have to be less than or equal to 150 here. That's the machine hours that are available here, 150 hours. Okay, and then for machine B, we also have some constraints. In case of machine B, only product Q is going through machine B, and it's using 1 hour, so 1 times Q here, and that has to be less than or equal to what? 50 hours here. That's all the capacity we have for machine B here. Okay, and just a note here, those are going to be fixed here in the short run here. That's why we can use our linear optimization here. We're just saying those costs are fixed in the short run. That's what we're looking at. And then we have those material and labors here. So let's look at our material here. Let's just go up and look at that here. Our material here, we have 1 for product P and 2 for product Q. And then our direct labor hours, we have 2 for P here and 1 for Q. Those are in hours and pounds. So just going down to our constraints here for material, 1P here plus 2Q. And this is the case here. When you're dealing with this material and labor here, you want to come up with the exact amount. So this is critical when you set it up in your linear program here. So what we have to do is we want to subtract out all that material here from the material that we're using here. So I've just got a coefficient of 1 here for the material, and that's going to be less than or equal to 0. We want just the exact materials here, and we'll look at why we want that. And same thing for our labor here. We're going to have 2 for P, 2 hours for P plus 1 hour for Q, and we want to subtract out our labor as well here, and then we have to set that less than or equal to 0. This is not fixed here. So really, why do we want to do that here? And we'll look at it. So if we go on up to our objective function here, it's really not a good idea to acquire more labor and material than would be used here. So that's what we're attempting to do. We're trying to get just the exact amount of material and labor, because we're subtracting those at variable, that is variable cost from our revenue here. And if you have more variable cost here for material and labor you're not using, obviously you're going to be reducing your contribution margin by the amount of extra that you have for each of those. Okay, so that's why we wanted to do that. So just to make a point here for the capacity constraints, this is our demand side, or that's the input that's used here. And then over here, our constraints, those are really the supply. That's the supply we have. In the case of the machine A, we have 150 hours here, machine B, 50 hours. But for material and labor, because we're trying to come up with those exact amounts here, we're setting those equal to 0. So that's critical for our linear programming here. And then, again, I've got it noted here as primal because we're going to be looking at primal and dual programs here. But we also want to look at the price, our product quantities here, plus our material and labor. We want them greater than or equal to 0 here. You don't want any negative amounts in this case, because you really can't have any negative amounts. Okay, so the total amount of input used or demand must not exceed the total supply of resources. So that's why we have this inequality here as less than or equal to. Here's our supply, here's our demand here. So demand or our input used can't exceed our supply. So that's the deal here. And just to make a quick point of it, I put this into a linear program here using MapleSoft, and I come up with a maximum amount here of $2,400 here. And then really what we want to look at, we've got a labor amount, material amount here, but product P, we're only selling 100 units here, and Q at 50 units. So really, the optimality here, the maximization, dictates which constraints are tight. And if you've gone back to our machining constraints here for A and B, if we plug those numbers in here, P and Q at 50 and 100, you're going to come up with, you're right on your capacity here of 150. And just looking at Q, you have 50 hours here, so you're right on its capacity here as well. Okay, so that's another key item that we're looking at here. So we said all the machine A and B capacity is used. So again, our profit here, that $2,400 would have to be reduced by that $100 of fixed cost to come up with our net profit. Okay, so that's for our capacity constraints. So now let's go up over here. So really what the linear programming model is going to tell us, and we're going to be looking at it, is how to best utilize our capacity that we have on those machines here. And that's assuming those machines are fixed here in the short run, because we can't add any machinery in the short run. So that's really what we're looking at, is the short run maximization here. And what we also look at is when and where we want to increase any capacity on these machines. When should we do it? Increase it here, and it should be when it should be expanded here, our capacity here, and at what cost. We have to deal with what cost. So that's what our linear program is going to tell us here. So we're going to be allocating our cost here to products for our capacity utilization. So again, what we're going to be doing here, because of this, we have 4 different variables we're dealing with. I want to boil those down to 2 variables, and then we can look at it in terms of graphs, or demonstrated on a 2D plots here. Otherwise, these extra 4 variables are going to cause us a problem. So let's just say here for our material and labor here, let's assume we're using all the material and labor, of course, what we're doing here. But what we're going to do here with this objective function that we've come up here with our material and labor requirements here, what we're going to do is we're going to take these constraint requirements and just put them into our materials here. So this is what we're doing here. So if we look at our material, go down to our objective function here, we're going to take that material here, which is 1P plus 2Q. We're going to put it in this at 10 times P plus 2Q here, and be subtracting that. And then for our labor, that $26 an hour here, for labor here, we're going to just take that labor, 2P plus 1Q off our constraints here and stick that in. And then after we solve for this, our equality is going to be, I'm not going to go through it all, it's going to be 14P plus 20Q. So what we've done here, all that variable cost is now included in our contribution margin. And we're not going to lose anything in the translation by doing that when we do our linear programming problem. We wouldn't normally be doing this, but just for our example here, for our further understanding, I'm trying to boil it down into these two variables here. So this is going to be our revised constraints. All we did is really chopped off our material and labor constraints. So our machinery constraints for A and B are going to say the same here. And then P and Q, those quantities have to be greater than 0 here. Okay, so we're going to continue on with our example here. So, but we're doing this here. I made this substitution here just so we can visualize this in 2 dimensions easily and understand what's going on. Now for our linear programming, we really have 2 different ways of looking at this problem. Either we can maximize the profit or the contribution margin that we're looking at, or we could minimize the marginal cost of the capacity here. So when you're looking at maximizing the profit, really you're looking at trying to define your optimal product mix here, trying to understand what that is. And then when you're minimizing the marginal cost, this is really what you're looking for, is when, where, and at what cost do you really want to expand any capacity. Okay, so we already looked at this problem here for maximizing our profit, where we have our contribution margin of 14 here for product P plus the contribution margin of 20 for product Q, along with those capacity constraints here for machine A and machine B here. So what we want to do is we're going to just take and convert this maximization problem into a minimization problem. So what you're going to do here is you just take that take your objective function here for that contribution margin, you just move that over into your minimization problem here, take the row here and essentially set it here as a column as your constraint here. 14P goes into product P here at 14, 20Q goes into product Q here at 20. Okay, so that's for the optimization here. So then the other thing for your capacity constraints, for machine A here, you just take that 1P here, that column, and you convert it into a row here for product P, becomes 1A here. And remember we had the less than or equal to here for our capacity constraints. Well, when you're talking about the minimization here, you're going to change that equality around to a greater than or equal to. And okay, we have that at 14. We set that here before from our objective function. And then for our other column here for Q1 and Q2 here for machine A and B, all you're going to Q1, except a 1Q here for each of those machines, you're just going to take this column and convert it into a row here, 1A plus 1B. 1Q becomes 1A plus 1P for product Q here, and then again that's going to be greater than or equal to 20. Okay, so what we've done here for the maximization, that's our primal problem, referred to as a linear programming primal problem. And again, remember everything's greater than or equal to 0 here. We have plus quantities here. And then for our minimization here, that's referred to as the dual problem here. And again, we're looking for those. These are really going to be weighted amounts here for the cost, and those are also got to be greater than 0, or we want plus prices. So with the maximization here, on the left hand side is really your inputs that you've used here, and they have to be less than the right hand side, the supply here that we looked at. But for the minimization problem here, the left hand side refers to the cost on a per unit basis. For product P it's going to cost so much here, and for product Q it's going to cost so much here, and those have to be greater than or equal to 0 here. That's what we're looking. And again, they have to be greater than or equal to 0, but they're based on, and don't get confused by this, this cost here really can't be greater than the benefit that we're going to look at, but let's understand that here. So let's go and look at that. On the left hand side it's the cost here per unit, and it has to be greater than the right hand side, the benefit. That's really illogical thinking here, but that's the way we set it up when we're talking about a minimization problem here. Really, the left-hand side, the cost here should never be greater than the right-hand side, the benefit. But that's just the nature of doing this linear programming. You have to put that constraint in that direction here, although it may be confusing. So let's just go back and let's look at this minimization here. So A here, it's amount A times 1. You just have 1 here times the price of A. That's really what we're looking at here. Plus Well, let's look at it for product Q here. That's just taking the amount of A here, whatever, that's a cost here, times the price, or quantity A is a quantity here, times the price of A here. And that's really what it represents here, plus the amount of B times the price of B here. We don't have those as prices and quantities, but we're going to just come up with one number here for each of those here. Okay, so we're looking at the cost per unit here of Q is greater than or equal to the benefit. That is not the case, but again, that's how we set it up for the linear programming. Again, left-hand side here, the cost should never be greater than or equal to the right-hand side, the benefit. These are the benefits here. That's our cost here. Okay, so what we're going to do here, we're going to solve the linear programming, and then we're going to go back to those constraint equations and see if we're using all the capacity. And really what you're looking to do is see if you're tight against the constraints that we've done here. Okay, so let's go up here, and I've solved this, and I've got it shown here in these plots here. Two-dimensional plots. That's why we reduced that equation or that problem from 4 variables down to 2 variables so we could see it. So this is our optimal solution here. So our maximization problem here, the maximization of our profit is shown here, and our minimization here, the cost is shown here. And our answers are shown here, where we have a 2400 is the value that we're looking at here for our maximum profit, or the maximization here of our contribution margin. And for our cost, this is just looking at the other side here. It's also 2400 here. So that's what we come up with our cost here. And really, these two have to match if we did those reversals here and we changed our maximization problem into a minimization problem. So we've got an answer here for each of them here that we're showing, and we'll look at those here. Okay, so first for our maximization problem here, I have the Q here, set quantity for Q set at 50, because that was the maximum amount we could make based on those 50 machine hours here that we have. We have 50 here. That becomes a constraint here. And then for P, we have that constraint here. It turns out to be 150 for those machine hours. Okay, so that's it. And then we also have this other constraint here. And really that red line that's downward sloping here, that is really the, if we've gone down and look at it, that's going to be this 1P plus 1Q here that is less than or equal to 150 here. Okay, so we really have 3 different constraints here. The quantities of 50 and 150 here for the machines themselves, and then that constraint here of 1P plus 1Q has to be less than 150. Okay, so what this problem is done here, we come up with a solution here, and just understand it. There's a blue line here, and that's really our profit line. That's the, you're going to follow this line up here from wherever it was. I don't know, it's going to intersect here. It looks like about 65, 66 or something. But what it does have here, and I'm showing the feasible solution. We could come up with any numbers in this green area here. Those are the feasible solutions that we have for this problem. And back to this blue line here, it really has a slope of 20 over 14. And that's really looking at this, our contribution margin optimization, or our objective function here, 14P and 20Q. So that's really the slope we're looking at. And when we did this problem, we're going to come up here with 100P that we're showing here in 50Q. That's the point here, that point that I've got circled here. And that's at the intersection here of all our constraints here, the 50 hours here for machine B, 150 hours here for machine A, I guess that is, and then the and then that constraint here with that slope of P plus Q, 1P plus 1Q here. Okay, so that's our maximum profit here. And the key is here, we have tight constraints, and that's going to be a key when we look at it with our tight constraints. We moved up against all our constraints here, both the machine hours for A and B here, plus the constraint we have on that combined amount for P and Q here. Okay, so that's for our maximum profit. Now for our minimum cost, it's just the opposite here. Our feasible solution I'm showing here in green here. And one other thing here, let's go back to these lines here, these gradient lines here. Really, those are perpendicular to that profit line that we're looking to, our blue line here. And really what you're taking at is you could slide along any one of these lines or perpendicular to that line here, and some mix on either side, or some mix between your P and Q in this case, will give you really the same profit that you're looking at here. Okay, that's what we're looking at with these perpendicular lines to that blue line. But the blue line is critical here because that's our maximum contribution line. You follow that line up and that gives us our maximum contribution at the constraint intersections here. And then for our minimization problem, again we're looking for tight constraints, and we come up with A is equal to A at 14 here, and B I'm showing here as 6. That's really a weighted cost that we're looking at here. Again, that's at an intersection here. This blue line, that's our minimum cost line. We follow that up or down, however you want to look at it. And really that's looking at the slope here. Remember that we're minimizing these total costs here, 150A plus 50B here. That's the slope here. We only go up with 50B and versus 150A here. And just over on this other side, just show it, we're going up at 20 Qs for every 14 Ps. So it's sloped up a little differently here. Okay, so again, this blue line is our minimum cost line. And the other thing is, again, we want to make a point here that this 6 here, this is going to be what they call a shadow price that we're going to be looking at. 6 here for B, and also the shadow price here is going to be 14 here for A here. Those are critical. But nonetheless, anything in this green area here is feasible. But what we wanted to do here in the case of the minimization here, we want to get the minimum cost that we're looking at. So you're working in just the opposite direction. Over here, we wanted to move up in the maximum amount here. Here, we're trying to move down in this direction, the minimum deal. So another key point, these are tight constraints. We come up against all our constraints here that in this case that was 1A plus 1B here, this red line that's sloping down here. And then we have I think what was it? We had a constraint here 14 on 14 here for A here, and then we also had, well, we have two constraints really here. This 14 here for A here, and then that slope here, 20 for B, if we went down and looked at our constraints down there. So we really only have two in this case here. Okay, so we come up tight against their constraints here. 14A, that's a weighted cost here, plus 6 here for B here. Okay, so this will come in handy now when we do our further analysis here. Okay, so now this is the other thing. This is here. Are the machine hours limiting, or should we increase our production here? Are we limiting our production here by the amount of machine hours? And yes, we did find that out because we were coming up with we used the maximum machine hours for A and B in both cases, for both A and B in our cases. So we are sitting at as much production as we're possibly can do here. So really what we have to do is we have to answer the question here. So what price should be paid to increase our contribution margin or increase our production here? And this is where we come up with a linear programming where we have a shadow price or a dual price. And that's what it costs for adding one additional unit here of our resource, really, which is causing the bottleneck. And that resource is in machine A and machine B here. Okay, so what we've done here, just looking at our maximization problem here, and then we had that minimization problem here. And really we'll concentrate on this minimization problem here for minimizing our cost that we looked at here. So what we want to look at is that here. So really this is what you want to do to determine that cost here on what it costs for each of those machines here to increase 1 unit or 1 unit of capacity here. So what you're going to do here first off, we know that our maximization program here was $2,400 here, and at P being 100 units, Q being 50. So what we want to do is we want to look at the case, and that's our maximization here. So to look at one more hour here by adding it to machine A here, or it was machine B here, that machine B, that 50 hours here. We're going to jack that up to 51 and leave that 150 here the same. So we put that into our program here. We just take and we maximize our program here, that total contribution margin here. But instead of leaving it at 50, we're going to put this in at 51, leave this at 150 with those constraints. Putting that in here, we're going to come up with the maximum profit here is going to be, our contribution is going to be $2,406. Compare that to the $2,400 that we have here, so we got a $6 change here. So that's going to be the cost of adding 1 hour here for machine B here. So we know that cost. And now for machine A, well, we do just the other thing. We take and we leave the 50 hours here the same, but we add machine A, we add 1 hour here up to 151 here. Okay. We put that into our program, and we're going to come up with our maximum profit here at 2,414. So we compare that to our 2,400 here, and again, it comes up with $14 for an extra hour here in machine B versus 6 here, or excuse me, for machine A here versus 6 for machine B here. And if we went back to that program here, remember we talked about that minimization problem? We come up with A at 14 and B at 6. That's exactly what we come up here with. Our just happens to be those who are the solving our equation here for that LP minimization solution. That just happens to be those costs here that we're looking at. And these are what they call the shadow prices here. Okay, so we've determined what our shadow price is, or our dual price, however you want to look at it. So if we went back here to our minimization, we could just put those in, and we could have solved it just looking at this here. So A, we had solved here at 14, and that matches our 14 here. We're saying it has to be greater than or equal to, but it matches here. And then if we know our A was 14 here, plus B at 6, that equals 20 here. So you see, cost of 1 hour of machine A here is $14. Cost of 1 hour here for machine B is $6, based on the equations that we have set up here, based on that minimization and maximization, using those figures here. Okay, so the machine, this is the key here. The machine A's benefit here has to be greater than $14 per unit here, based on that adding that one additional hour here to machine A. We have to have a benefit. We have to earn $14.01 more here, or whatever. It has to be greater than $14 here. Otherwise, it makes no sense to expand the capacity. We have to have that benefit here. So we have to determine, is that what we can deal with here when we're adding that extra capacity? Are we going to earn that much? And for machine B, it's $6 per unit here. Again, same as we solved for our minimization problem. So, all right, so that's what we know. So knowing that here, then you can decide, is it worth making that expansion, adding more capacity, adding another machine, either buying or adding some additional capacity here for machine A and machine B. And just remember, those are for product P and Q here. Product P is only going through machine A. Product Q is going through machine A and machine B here. Okay. All right, so we've got that. So now we can further go and look at how we can handle this problem here. We're going to look at the case here where we're going to find out that we really don't have the optimal solution here. So we're going to not be coming up against our constraints. So what we're going to do is we're going to further move on here. We're going to change our product P selling price here from $76 up to $90. And we're going to just throw it into that linear program that we just went through for our minimization and maximization here. So this is the case here. When we do that, when we move that selling price up to $90 here, now we're saying we should make 151 here P and 0 Q, none of Q here. And then if we put it in for the minimization here, we're going to come up with, and you can see 42.28 was our profit here, and for our minimum cost, we've got 4,200. It's a little different here. But what the key is here, when we come up with 0 here for Q, product Q, because of that price increase here, we're also coming up with the deal here. Q is really, the B, that B machine here. I'm showing a real small negative number here, but it really should be 0. So this is the key here. You're not running up against the constraint here, and we're going to look at that in we're looking at that two-dimensional plot here. But this is what you want to look at. You want to look for those zeros here when you expand those capacities or do any of your changes here to either your demands or your benefits or your supplies and so forth, or changing the objective function. When you want to do that, then you want to start looking at those different quantities here to see if you're ending up, if you're bumping up against your constraints here. So really the rule is you must be using the capacity constraint, you must be using some of that capacity constraint or bumping up against those constraints here as you would guess here, before increasing any capacity here. So if your machine hour constraints were not tight, then really you shouldn't be increasing any capacity. That is not using the machines. Therefore, there would be no benefit to add capacity, as you're going to be we'll look at it in the last case here, where the price was increased here. Again, we want to check for zeros for those different products, and also those costs that we minimize cost here. So you want to run a linear program, and you want to check for your constraints to see if you have a benefit here. But at least what you want to take away from this is based on that linear programming, you get an idea of what your cost of increasing that capacity by really 1 unit here in both cases. We're looking at machines in this case. So if you can deal with earning more, you have to earn more money than your cost here, otherwise it makes no sense to do it. Okay, so we're going to further go over here, and we'll just end up by looking at this case here, where we end up with Q, 0 products here for Q, not building any here for Q, and also coming up with 0 here for the machine capacity. All right. Okay, now we'll look at our solution here where we change that selling price. But before we do that, let's just look at our initial optimal solution here for our maximum profit here and our minimum cost. So remember, I talked about those tight constraints. We came up against those constraints here, so we couldn't produce any more here because we're tied up against those constraints in both cases here. And the case is, when you have that optimal solution here, your minimum cost should really equal your maximum profit. And we show that $2,400 here for a maximum profit versus a minimum cost here at $2,400. Okay, so that's the case. And we came up against those constraints here. And then one other thing here for this initial solution here for the minimum cost, we talked about those shadow prices here, and that's the price that you have to pay for 1 more unit here or time here for machine B. We came up with $6 here, and machine A, we come up with $14 here. And that's only because we had that optimal solution here. Okay, so now let's move down here and look at the case here where we have this, we're based on that, changing our product P here, the selling price from $76 up to $90 here. Okay, this is what we have for our maximum profit over here and our minimum cost here. And just look at our solution here. We come up with what our costs are over here. But the key is looking at the fact that we have 0 of product Q that we should be making, and we have no usage of machine B here. So that's the key to it. Okay, so looking at our maximum profit here and minimum cost. First off, let's just look at the solution here. We're sitting way down here at P. We come up with 150 here at P, 0 here for Q here. So you can see we're not up against our constraint here. And then for our minimum cost here, we're sitting again here for A here, we're sitting at 28 here, 28 units here for A, 0 for B here, just to make a point. So you can see we're not up against our constraints here. We're not tied up against our constraints because we have those constraints. If we looked at them here for the maximum profit here, we had that 50 for machine, or 50 here for Q, and what is 150? Well, we have this constraint here. P plus 1Q has to be less than 150 here. That constraint plus those other 150 and 50 for the machine hours here. But we're sitting here 0Q. So when you do these problems, you want to lay these things out. And whatever your constraints are here, all these constraints can change here. In this case, I didn't change any constraints. I just changed the price and left it as is here, the constraints. But you can see, we're not using any, we're producing none of Q here, so why would we're not using any of the machine B capacity, so you're not going to want to change any machine B capacity here. And A here doesn't make any sense either here. So what you want to do here, unless point is here, maybe be impractical here, but you really want to be selling some of Q here and some of T here. You want to come up with that optimal amount here. But just to make a point here, again, with the minimum cost, we have this, our constraint line here, 1A plus 1B has to be less than or equal to, or greater than or equal to 20, showing it here. And then we have that feasible area here. We have that other constraint was $14 here for, 14 here for, we moved it up here to 18 in this case here, because that's going to be our new contribution margin here. So we laid out a new constraint here, and we moved down on the line here. So if we moved up here, you can see we're sitting here at 14, and it just happens to be that I know we changed A here by changing that price here on the from 76 to 90. I moved up from A here from 14 up to 18 here. I know that's what I saw there. I should be showing it. But nonetheless here, that's what you want to do here. Whenever you make those changes, you want to lay out your constraints, and you want to see if you're at some, you're bumping up against the constraints here. In this case, we aren't. So there's no benefit to increase any machine capacity here in B. We did it here visually, and really probably the best way to look at it is visually here to get some good understanding of what's going on. Okay, so that'll end our discussion.